Building modern software is a lot like constructing a digital skyscraper. If you want to build something that reaches the clouds, you need materials that are strong, flexible, and easy to work with. That is exactly why developers rely on Python. It is the ultimate accessible construction tool for the digital world. This table outlines exactly why Python is popular. Under the Features section, it highlights that Python is an interpreted language. This means the computer reads your code line by line as it runs, much like a chef reading a recipe while they cook. You don't have to compile or translate your entire project into a complex computer-only language before you can see it work. You just write and go. As you can see in the applications list below, that simple approach powers everything from artificial intelligence to web development. To set up your own workspace, you simply download the latest version from python.org. During installation, there is one crucial box you must check: Add Python to Path. That ensures your computer's command line knows exactly where your new tools are. After that, you pick an Integrated Development Environment, or IDE, which acts as your digital workbench for writing code. This comparison table breaks down how to name your basic storage containers, which we call variables. Variables hold your building materials, like text or numbers. Python uses dynamic typing, meaning you don't have to announce what kind of material you're storing. Python figures it out automatically. You just have to follow strict naming rules. They are case-sensitive, they can't start with numbers, and as the table shows, special characters aren't allowed except for underscores. Looking lower, Python allows you to assign values to multiple variables all on a single line, unpacking different values into a row of containers simultaneously. Because Python handles the heavy lifting of figuring out data types and translations, you don't have to micromanage your raw materials. You are free to focus entirely on the architectural design of your program. Once you have your materials, you need rules for how they interact. We use operators to do this. Arithmetic operators handle the math, comparison operators weigh values against each other, and logical operators combine different conditions. Think of them as the traffic lights of your logistics network. This hierarchical diagram maps out how we route data through our program using control flow statements. On the left side, we have decision-making checkpoints. Using if, elif, and else statements, your code can evaluate a situation and choose to travel down completely different paths based on the information it receives. In the center of the reference sheet, you'll see examples of iteration. Loops are your automated assembly lines. A for loop will repeat an action a specific number of times, while a while loop will keep churning indefinitely as long as a certain condition remains true. By combining these routing checkpoints and assembly lines, your code transforms from a static pile of variables into an active, dynamic system that makes its own logistical decisions. As a project grows, building every single room from scratch becomes impossible. To scale up, developers stop laying individual bricks and start using specialized tools and pre-made rooms. This syntax box introduces functions, which are reusable blocks of code dedicated to a single task. You feed raw materials into the function using parameters, and it passes the finished product back out using the return keyword. You can even include a docstring explaining exactly what the tool does. Looking at this list comprehension chart, we see a highly condensed way to process those loops we talked about earlier. Instead of writing multiple lines to filter and sort data, a list comprehension packs the entire assembly line into a single, highly readable set of brackets. It processes and filters data in a fraction of the time. This table outlines built-in modules, which are entire files of pre-written code. By simply importing modules like math, random, or datetime, you instantly bolt complex, fully functional prefabricated rooms onto your project without having to write the underlying logic yourself. Functions and modules form a massive collaborative ecosystem. Developers share these tools globally, allowing you to scale your software infinitely by building on top of the work others have already perfected. When those projects become truly massive, functions and variables alone aren't enough to keep things organized. We need a master architectural floor plan. That structure is object-oriented programming. Object-oriented programming hinges on two concepts. A class is the abstract blueprint. It defines the rules. An object is the actual physical house built from that blueprint. You can build hundreds of unique houses from one base blueprint. This code snippet demonstrates how we build those objects. The init constructor acts as the setup crew for a new object. By using the self keyword, the code ensures that specific attributes, like a student's individual name or age, are permanently attached to that specific instance, rather than floating around the program. Below that, we see inheritance in action. A child class, like a dog, can automatically absorb all the traits and abilities of a parent class, like an animal. You only write the shared behaviors once. By organizing code into neat, self-contained objects that share traits intelligently, software systems can grow to millions of lines long without collapsing under their own weight. Before a building opens to the public, it has to be reinforced. In the real world, software encounters missing files, bad user inputs, and overwhelming amounts of data. This snippet shows Python handling outside documents. The with open syntax guarantees files are safely closed, preventing data corruption. Above, exception handling acts as a safety net. A try block tests dangerous actions, and the except block catches errors to keep your application running. When handling massive data, we compare iterators and generators. Standard iterators load everything into memory at once. By using the yield keyword, a generator produces one piece of data at a time. This keeps your memory footprint flat, regardless of data size. Implementing proper error catching and strict memory efficiency takes a script that works on your laptop and turns it into a robust application ready for a global audience. With the release of Python 3.14, the language receives a series of updates that modernize how it thinks and talks to your computer. One update provides a simpler way to mix plain text with your data, making your code easier to read. It also introduces a read-it-later approach for the labels and notes you put in your code. Previously, Python had to read every single note before it even started the program. Now, it skips that heavy background reading until it actually needs the info, so your program wakes up much faster. Most importantly, 3.14 makes it easier to use multiple sub-interpreters. Instead of your complex tasks waiting in a single file line, you can route them into multiple synchronized lanes. This enables true parallel processing, allowing heavy computations to run simultaneously. It also includes native support for Z-standard compression, meaning data storage and retrieval is now highly optimized right out of the box. From its simple, readable syntax for beginners, all the way up to advanced parallel processing architecture for experts, Python is designed to scale alongside you perfectly, from your first line of code to your 10th year in the industry. To cement today's concepts, pause the video and work through the interview questions and coding exercises on screen. Practice is how the logic truly sets in. I'll see you in the next module for advanced asynchronous programming. Keep coding!